Okay, so now let's look at the laws of chemical change. There are quite a few laws here, and they govern everything in chemistry. They're quite simple laws, but they're going to rule everything. So the whole basis of this is reactants go to products with this arrow here. For instance, sodium plus chlorine in a synthesis reaction makes sodium chloride. Okay, here is a model of something happening here. If you look at this, here comes this little atom, and it goes and attacks this other compound that was here. See this compound, and then along comes this atom, and you can see that these two are effectively swapping partners. The little green ball gets this ammonia thing here, and the little white ball disappears. The little yellow ball disappears off into the sunset. So there were bonds in the beginning of this. There's a bond here, and that bond gets broken, and a new bond forms with the little green ball. Okay, so in a chemical reaction, reactants go to products. This is the reactant, this is the product, and bonds are broken and new bonds are created. So the first law that we need to know, we've discussed this before, and you are all familiar with my joke, okay, is the law of constant composition. So this says a specific chemical compound always consists of the same elements in exactly the same ratio. So H2O, we go to the kitchen and we pour it out the tap and we drink it and we have a continuing good day. H2O2, look here, hydrogen and oxygen, the ratio is different. This is hydrogen peroxide. We drink this and end up in the hospital. Okay. Also, carbon monoxide versus carbon dioxide, a 1-to-1 ratio, a 1-to-2 ratio, but this is carbon and oxygen, and this is carbon and oxygen. They are not the same. If you breathe in too much carbon monoxide, you will die because it bonds to all of your hemoglobin in your blood, and then the oxygen can't bond and you just die. This is what often leads to suffocation. Okay, so they are not the same things just because they have the same atoms. What chemical compound you are depends on the ratio of your elements, and this is called the law of constant composition. The next law we want to look at is the law of conservation of mass. Okay, so this says the total mass of the particles before a reaction and the total mass of the particles after a reaction will remain constant. And remember, this is because the atoms that are on the left are the atoms that are on the right. However, the molecules on the left can be different from the molecules on the right. But in a chemical reaction, we are not doing witchcraft. If there's sodium and chlorine atoms on the left, there are sodium and chlorine atoms on the right. If there are hydrogen and oxygen atoms on the left, there are hydrogen and oxygen atoms on the right. We cannot, unfortunately, turn lead into gold. So this is the summary of this. Reactants go to products. The types of atoms in reactants are the same as the types of atoms in the products. The number of atoms in the reactants is equal to the number of atoms in the products. So the mass before the reaction is exactly equal to the mass after the reaction. Now you have to remember all of this because they're going to make you do sums with this. So here is an example of the sums. This reaction here, hydrogen plus nitrogen goes to this compound here, which is ammonia, which I hope you've memorized. This chemical reaction is called the Haber process, and it's actually reversible. That's why it's got these weird arrows, but for our purposes, we will look at it as a non-reversible reaction. Okay, this reaction, hydrogen plus nitrogen goes to ammonia. You'll see it quite commonly because in grade 12, you discuss how to do this reaction in industry. It's called the Haber process. But for now, let us have a look at this in relation to the law of constant mass. Okay, so this is the balanced equation. There are 3 hydrogen molecules, 1 nitrogen molecule, and you end up with 2 ammonia molecules. So in pictures, hydrogen, hydrogen, hydrogen. Can you see I've got 3 diatomic hydrogen molecules and 1 diatomic nitrogen molecule, and on the other side I've got 2 ammonia molecules. So if you look on your periodic table, okay, hydrogen weighs 1, nitrogen weighs 14. Look, here's your periodic table. There's the hydrogen and there's the nitrogen. So if we were to prove the law of constant mass, which they often ask you to do in exam questions, we have to take this capital M, the mass of nitrogen, plus the mass of the hydrogen, and check if it equals the mass of the ammonia, which is our product. So in general, you'll take the mass of the reactants and see that it matches the mass of the products. So each of these little hydrogen atoms from the periodic table is going to weigh 1. So 1, 2, 3, 4, 5, 6. You can see over here it's got here 3. Where did this 3 come from? It's this 3 from the balanced equation, okay, because everything depends on the balanced equation. If the equation isn't balanced, this won't work. So I've got here 3 hydrogens. So it's 3, and there are 2 atoms because it's a diatomic molecule. 3, 2 times 1. Here's my hydrogen mass taken care of. And then from the balanced equation, there's only 1 nitrogen molecule, and it's made up of 2 nitrogen atoms, so 2 times 14. So here is the nitrogen. 2 times 14 is 28. 2 times 1 is 2, times 3 is 6. So 28 plus 6 on the left. Now let's look on the right in the products. We have nitrogen, hydrogen, hydrogen. So there is from the balanced equation 2 of these. So what is the mass of 2 ammonias? It's 2, and then the nitrogen here in 2 for the 2 molecules. The nitrogen here is 14 plus 1, 2, 3 hydrogens. So 14 plus 3 hydrogens. So 14 plus 3 is 17. 2 times 17 is 34. So here 28 grams of nitrogen plus 6 grams of hydrogen will go to 34 grams of ammonia. So the left-hand side equals the right-hand side, which means the law of conservation of mass has been proved based on the chemical formula of the compounds and the coefficients in the balanced equation. Look, here's another example. This is the synthesis of water. Okay, 2 hydrogen plus oxygen goes to 2 water. So look here, 1, 2 hydrogen atoms, 1, 2 hydrogen atoms. It's a diatomic molecule. 1, 2 oxygen atoms, also a diatomic molecule. So these bonds are broken between the hydrogen and between the oxygens, and they reform as 2 water molecules. So now we need to check their masses. Remember from the periodic table, hydrogen was 1. So I've got 1, 2, 3, 4. 4 times 1. Plus my oxygen is O2. A single oxygen atom weighs 16, so 2 oxygen atoms is 2 times 16. And then we have water. So water is 2 times the mass of hydrogen, which is 1 plus 16. So inside the brackets here you'll have 18, and 2 times 18 is 36. This is 4, this is 32, so 4 plus 32 equals 36. The law of constant mass has been proved. Okay, now there's one more law that I want to talk about. We need to know this law, Avogadro's law. There's a law of volume. So think of these as balloons filled with gas. Okay, and we're going to learn about moles later on. Chemists always love to talk about moles. But Avogadro's law, which we'll talk about again later, tells you that if you have a specific number, say 5, so say if I've got 5 particles of any gas, they are going to take up the same volume if the temperature and pressure are not changed. If the temperature and pressure are fixed, so say at room temperature, and I've got 5 particles of hydrogen gas, 5 particles of nitrogen gas, 5 particles of methane gas, they will all fill a balloon to exactly the same size. This is called Avogadro's law, and later I will see if I can give you the exact definition of Avogadro's law. The problem is Avogadro's law has the word mole in it, and according to the chemistry curriculum we haven't defined moles yet, but hopefully we will get to moles soon, which will make this more interesting. But for now, the law of volume of gases says that a specific number of particles of any gas occupies the same volume at a fixed temperature and pressure. So here's the example of this. If you've got sulfur dioxide and oxygen going to sulfur trioxide, if you've got 2 particles of sulfur dioxide, it will be 2 volumes of sulfur dioxide, and it can be this unit that we use to measure volume, a cubic decimeter. And if we then react them, this 2 sulfur dioxide plus the oxygen going to 2 sulfur trioxide, you will always have 2 particles of sulfur dioxide plus 1 particle of oxygen will go to 2 particles of sulfur trioxide. And these sort of relationships, these gas relationships, are also how people learned things in the periodic table. And we're going to be using this cubic decimeter a lot. So 1 cubic decimeter, this 1 dm3, works out as 1 cubic decimeter, which is 1,000 cubic centimeters, which is a liter or 1,000 milliliters. So sometimes they use these cubic centimeters and milliliters interchangeably, but a cubic decimeter is just a liter if you want to visualize it. And that's where the end of this topic lies for now, but we have not done calculations, so we need calculations to prove all of these.